All right. Good morning, everyone. So let's get started. We are about to conclude the topic about structure formation. Okay, so we are going to second order during the last lectures in terms of perturbations. And we arrived at discovering what are the subtleties in the overall formation of structures across the universe, right? We started in the linear regime, and that was enough to describe, for example, the cosmic micro background fluctuations, right? We derived the fully relativistic equations that allowed us to describe matter and radiations as well, okay? And combination of the two. Together with the effect of gravity, and for the expansion of the universe is considered, as well as the local fluctuations in the potential. Okay? Right, and then we discovered also that there is a difference in how we treat things. We define two different regimes, outside the horizon and within the horizon. Okay, so the set of equations that I gave you are completely general. So they are valid also, let's say, next to the horizon on both sides, so that's fine. But we went into depth into the two distinct regimes, into two distinct limits. Why we did that? Well, because outside the horizon is interesting, but not that interesting. But that's interesting if we want to know, for example, what is the effect on the evolution of the fluctuations across the time on large scales. And this has an impact on the final power spectrum, through the transfer function that we studied during cosmology. And within the horizon, on small scales, that's very relevant because that's the approximation that we use to describe these sort of fluctuations. Okay? Here we are at early times, still quite early in terms of the evolution of the structures, and we are in the linear regime. So the fluctuations that you see here, we transfer the energy density fluctuations of the photon fields into a temperature fluctuations. That's because that's what we measure with Planck, for example, in the millimeter regime, or with the South Pole telescope, or these other millimeter instruments. And you see there are different blobs, and what is the size of the blobs, on top of which you can see there are larger modes. Okay, so you can see the modes of the blobs, these are high frequencies, high modes, and then you have fluctuations on larger scales. And in fact, you see that there is a sort of coherent pattern that is going, for example, from large, small, large, small, large, small, and so on and so forth. These are low frequency regimes. Okay? Then what we did was, okay, that's interesting, we have the equations to characterize these sort of fluctuations, but we don't care about knowing, okay, I have a hot spot here, a cold one here, another hot here, and so on and so forth. We don't need to know each individual location, what's the temperature there. We can characterize all of this mass through the power spectrum. Okay? In the linear regime, the power spectrum, if the initial conditions are Gaussians, so we have Gaussianity, is enough to characterize completely this mass. Okay? The power spectrum in the linear regime, and assuming Gaussianity for the density fluctuations, give us a full statistical description of the cosmic micro background. Okay? Then what we have seen, that the universe is evolving, we might have over-densities which reach the critical regime for the collapse. And there the density grows. Okay? Here the growth, again, is in the linear regime, and therefore the modes are still decoupled. Okay? Each mode evolves independently. And if you remember the equation that we had for describing the fluctuations in the energy density fields, we had something. Now I sketch it, I don't write all of it. We had double plot plus something, double prime, plus something, and delta. So these are the fluctuations. So I always use this sort of delta, the curve delta equal to 0. Okay? So you see that's equal to 0. It means there are only linear terms here. And we have a damped oscillator, okay, with a friction and an oscillation mode. Okay? Nice. And that's for K, K, and K. Right? The modes are decoupled, fully decoupled. They evolve independently. The power spectrum, as it evolves, is not going to change shape. It's just going to change its amplitude. And in fact, in the linear regime, everything is characterized by the growth function. Right? The growth function is a linear term. Of course, we have the fluctuations as a function of time, so that's the time evolution, is some initial fluctuation, and then we have the growth term that captures the time evolution. Here, a growth time, I could have written as well as a function of A, as a function of n, or as a function of redshift. Okay, so they're just different variables that help us to characterize the time evolution. Okay, so you see, the growth factor characterizes it. So you understand that the growth factor is a monotonic growing function, because the structure tends to grow, if what? If the initial condition is this one. Because here we would have a plus, that's a growing function, delta is going to grow, right? But, and for example, maybe an overdense region, then overdense region tend to grow. If the initial condition instead is this one, we have an underdense region, then its density is going to decrease. And why we have that? Well, we expect that because of the continuity equation. If we have an energy density that describes the energy density flux, right? Therefore, we are going to have fluctuations of this sort, where these guys are going to grow, and these guys are going to get smaller and smaller, smaller and smaller. Why? Because, smaller and smaller. Why? Because we have an energy density which gets transferred in other locations, right? That's the continuity equation. So we have, this tells us that we have low modes that are going to decrease and others that are increasing. That's because there is an energy density flux. That's the core. That's the physical idea. Okay? Nice. And each mode, as I said, evolves independently. Now what have we seen when we went to the second order? Okay, this was perturbation at first order. For example, we had like the density field, and it was characterized by the background plus a tiny fluctuation, right? First order. Then we went to second order. And when we went to second order, the equation didn't have this structure anymore. There was, okay, delta blah blah blah, and so on and so forth, but then there was an integral. There was an integral with respect to different k modes. Where we had the function that we were characterizing in terms of fluctuation, for example, the density field. We have rho and rho, for example, rho and theta, there are various combinations, doesn't matter. So we had a function and a kernel coupling. The coupling kernel at the first order, coupling one modes to another one. Right? We have an integral, and there was a delta function, but that's not relevant. Okay? What I'm stressing is that an integral is popping up here, coupling modes. Okay? In the nonlinear regime, modes are coupled. And therefore, the fluctuations are going, so if the fluctuation with a certain frequency and fluctuations with another frequency, so higher frequency mode and low frequency mode, are kind of talking one with each other. Power that is captured by one mode can be transferred to the other one. The shape of the power spectrum is going to change. Okay? That's, across all the mathematics we did, that's the key difference between linear and nonlinear terms. Okay? Nice. Good. Now that we have that, we can continue with our path. Of course, this decided to go none. Okay. Then the universe is evolving, right? As a function of time, the structure growth. Of course, here we don't see anything because I'm going to show you yet a numerical simulation with a better visualization with respect to the other time. That's all for the dark. Okay, and here you cannot perceive it, but from here I can see it. There are tiny fluctuations. Remember that the fluctuation of the CB, temperature fluctuation of the order of 10 to the minus 5. Okay? So a fraction of a per minute. So very small. Matter is doing what it has to do. I don't see the mouse. Do you see it? If I do like this, yes, it's starting. Great. Now the time is growing. Well, it's really dark. You see, dark is dark. Let's go in cinema mode. Okay, like that. Oh, now we can see it. Okay, so you can see that now there are fluctuations that are perceivable. In here, we are already in a non-linear regime on small scales. Look, there is a dot here, a dot here. This one you can clearly see that, right? So these are non-linear structures already. These are collapsed hills. Okay? Highly non-linear regime. But on large scales, we are still in the linear regime. Okay? So it's not that you are going to use the linear regime only at high redshift. Okay? You can also use it at low redshift. Redshift 0.3, not 2000 simply. Okay? And you can do it only on large scales, because the large modes are still in the linear regime. Okay? So you can use all the theory that we use up to a certain level. When we went to second order, you know, we are in the mildly non-linear regime, and you can push your estimates to smaller wavelengths, to smaller K modes. Okay? To smaller regimes. Let's say not on that scale, but you can study fluctuations on a lower regime. Okay? And as the universe is evolving, as the field is getting more and more non-linear, you need to keep more and more higher order terms. Okay? What's the problem? The problem is that if we work at second order, yeah, the mathematics can be done. And you say, let's go to third order. Yes, the mathematics can be done. If we go to fourth, fifth, and so order, things explode. Okay? Equations get very unstable, and to keep the numerics controlled and all the equations controlled is basically unfeasible. Okay? Nobody goes in this direction. Other techniques are in place. Okay? For example, numerical simulations, which is a brute force approach. We've been content already in the past semester, where we just use basically Newton's law. Okay, it's really brute force approach. We have Newton's law, G N over R to the power of 2. That's the force that we're going to use, that's the modulus, right? Between one particle and another particle. And if there is another particle, we need to compute the force of this particle given by the 2. And so on and so forth, and you do it for a billion of particles. And with billion of particles, I don't mean an atom, okay, a dark matter particle, but I mean a huge chunk of the universe, say with a mass, so the mass of each particle is of the order of 10 to the 6 solar masses and sun. Okay, so a chunk of the universe. Okay? And then just brute force approach, of course you incorporate the fact that the universe is expanding and all of that, and you get basically this sort of movies that gives you a very detailed description. Okay, so let's go. You see structures are forming. You see it's also spinning. We are spinning across the universe, but you see that they are getting stronger and stronger. Look, filaments are getting formed. Okay, look the density how it's growing. It's getting redder and redder. Look these ones. These are galaxy clusters. See all these blobs? And merging is taking place. So if you follow this guy, you see that matter is flowing into it. Okay, there are blobs that are falling into it. Okay, that's this hierarchical formation of the cosmic structure. Look at these big ones. We have two big ones. They are going to merge. Okay, filaments are getting stronger and stronger. You see the field is getting more and more nonlinear. Okay, so you see on this scale now, forget about the linear regime. Forget about the second order, the one loop that we consider. You need much larger scales. Look how many blobs were present here at the beginning. Now look, we just have a gigantic halo that is getting larger and larger. Not indefinitely, because each term has its own kinetic velocity that keeps them orbiting around the central object. Okay? In the context of what you showed us about the formation of galaxies, you see that within galaxy clusters, now we can see a galaxy cluster formed, there is a gigantic galaxy in the middle. That's called CD galaxy, central dominant galaxy. Okay? And they are ellipticals. The ellipticals, which are passively evolving, or most of them, basically, almost the totality of them is passively evolving, meaning they are not producing stars, because all the gas have been already burned and produced all the stars. Okay? And they look red. Okay? Within the core, in the central parts, there are other ellipticals, and then there are also blue ones, which are still star forming, but they orbit on larger radii. Okay? They are scattered across the entire halo, constituting the baryonic content of the particles of the galaxy cluster. Okay? Therefore, you see that within galaxy cluster we tend to have redder galaxies, and outside galaxy cluster we tend to have blue galaxies, which are the typical galaxies that we find also across the field. So outside galaxy clusters you tend to find blue galaxies. Why I'm mentioning this? We are going to astrophysics, and I'm talking about astrophysical process. Why is this relevant for cosmology? Because when we observe this stuff, we don't see the density field. Okay? What we see, let's stop this guy, otherwise we will have commercial for the entire lecture. Let's move to that. What you see is actually are actually galaxies. Okay? Are galaxies. The galaxies are tracers of the fluctuations. They are not the fluctuations themselves. Because what is constituting most of the matter across the universe? That's dark matter. Okay? We have dark matter. And we can see dark matter through, for example, gravitational lensing. Why? Because gravitational lensing is sensitive to the potential at a certain position integrated along the line of sight. This we measure. It's a direct observable through gravitational lensing measurement. So we can map the density field. Very clean observable, very little astrophysics involved. That's why it's one of the most powerful we have. Then we have the galaxies. We have the galaxies, and if we have regions that are denser with respect to others, okay, let's say that this chalk white represents the true matter fluctuations, what we actually observe are the galaxies where we expect to have more galaxies here, because there is more matter, and therefore more galaxies can form, and few in the underdense regions. Okay? So how do we do that? Well, the easiest thing to do is to define a bias term, in which we say, okay, I have my fluctuation of matter, so that's the entirety of the matter fluctuations, what we predicted with our equations, and we have the density fluctuations that we measure for the galaxies, and we just multiply a bias term, which capture all the astrophysics that transfer the total distribution of matter into points, into galaxies. Okay? From the total distribution of matter, including baryons and dark matter across the universe, there is all the astrophysics that we have seen with feedback and all the mass that give creation of stars, is captured here. Okay? And we can fit it. If we go linear regime, that's not enough. If we go at the higher order, then we can have, for example, a Taylor expansion. Okay, so we have one bias term plus another bias term, and for example, it depends on the power to the fluctuations or other variables. Okay? Delta plus P2, and then delta to the power of 2. Plus, people realize that other terms are necessary. Okay? That's the entire picture. That's the entire picture if you want to study the density fluctuation through galaxy clustering. Okay? So that's the scheme. I will now recap what we did last time through the equations, and then we will continue and arrive at the end and characterize everything in terms of bias, plus additional corrections that we'll have to include for our analytical prescription at the second order. Okay? Good. So let's do that. Okay, that's enough in terms of darkness. And let's give a look. Provided. No. Yep.
Sorry.
Yeah.
Can we lift up the blind just to get more air in?
Yes, that will be useful. Okay, and I will also open that array. That's nice. Okay, good. So that's what we did last time. So we started with the hydro equations, including the Poisson equation. So we restricted ourselves to the Newtonian regime. So it's not fully relativistic, but it's an extremely good approximation for within the horizon for small k modes. Okay. Then we did all our mathematical machinery. We introduced the perturbations including also second order, and we arrived at this perturbation equation. Okay, that's full. Okay, no approximations are done. And we identify the terms that are coming from the linear regime. So in the linear regime we had this guy equal to 0. Now we have the higher order terms that pop up as these ones. Okay? And then to make our life a little bit simpler to get a clean mathematical derivation, we restricted ourselves to the Einstein de Sitter universe, where all of these terms become like that, just because we are considering a matter-dominated universe. And I told you that if you would use a generic cosmology, then you will get basically this result with a slightly different number. Okay, so it's an approximation, but it works very well. Okay, good. Then what we did, we start to expand. These were all the linear terms. As I said, no approximation has been done in terms of expansion of the perturbation. Now what we want to do is to not linearize this equation, but do a similar path to what we did when we derived the linear regime. Okay? But this time we keep second order term, not only first order term, that are introduced like that. Okay? So we have a growth factor. A growth function that is referring to the linear mode fluctuations, and a growth factor, another growth factor that carries the second order information. We plug these guys into our equation, like this one, for example, that's the continuity equation, so you get your delta, you plug it here and here, same goes for the velocities, and you arrive at this expression. Okay? Then, no magic is done here, but you already see that there is the integral I was mentioning earlier. Okay? That provides the coupling between one mode and another mode. In the linear regime, already at second order, you have mode coupling. Okay? That's extremely important. Then there is a little bit of machinery, we go to Fourier space, we come back, and so on and so forth, and we arrive at the continuity equation that can be written in this way, and the Euler equation which is written in this way. Okay? That's what we did during the last lecture. And again, I stress the fact that in the final results we had what we had, the continuity equation in the linear regime, if we would have a zero here. Here we had the terms responsible for the mode coupling. Same goes for the Euler equation, in which we had the linear regime equation, if this would be equal to zero, but now we have a mode coupling given by this kernel. Okay? One kernel, you see that's C and that's E, so two different kernels for these different equations. But you understand that whatever we are going to do also for the other equations, we are going to get this sort of structure. Linear regime, correction with an integral with respect to k modes, a kernel, and then the quantity we are integrating over, and the delta function. Okay? Always this structure. You see these two equations have exactly the same structure. Good. Now what we did, once we have that, we start to solve our equations, means we get, that's exactly as you do with in the linear regime. You get the equation E, the first one, you get its derivative, and you plug it into equation B. Okay? You can see it easily here. There is a V prime here, a V here. So we make the derivative of this equation, so that such that you have an expression for V prime, and you plug it into here. So you solve your system of equations. A little bit of reshuffling a few terms. Again, you keep terms up to second order, and you arrive at this equation. This equation, which is solved by that. Okay, so that's the general solution of the problem. So we have our solution in an analytical form. Okay, there is an integral to be solved, but still that's your analytical expression for the power spectrum. Sorry, for the fluctuation. Okay, nice. And yeah, basically that's it. Then, so this is sort of generic, because here we made just a Taylor expansion. Then as a last step, we reapply our Einstein de Sitter approximation. So we're considering a matter-dominated universe, and this G prime, G second term become like that. So it's very simple. We plug it into here, and that's what we get. Okay? So these are the explicit solution for the density fluctuation and the velocity fluctuation, the perturbations at second order. Okay? That's what we have. We got our delta 2 and V2. Nice. Later, I'm going to conclude this part of the derivation, and we are going to compute the power spectrum, which is just obtained by computing, by averaging different realizations, or using the ergodic principle over different chunk of the universe that are independent one from each other. We just plug in our solution that includes the first order term and second order term. And we will discover that actually we will also need go to the third order for the power spectrum, but this we will see it later. Okay? Good. I will continue here because the equations that we're going to obtain are going to blow up. Okay, so that's what we were left. And here we have the derivation for the power spectrum. Nice. So, what do we have here? We have this quantity that we want to compute because this is an observable. Okay? We can relate it to the distribution of galaxies and we can measure it. So we are going to define a quantity, this P, that is based on the fluctuations. Okay? Coming from T. So that we have a link between observations and T. So what we have? Well, we have a definition of a power spectrum, so whatever function you have, that's an average with respect to to different realization from statistics. In practice, we have used the ergodic principle where we are considering different chunks of the universe as independent. And you just have the function in the Fourier space times its own complex conjugate. And by construction, that's the amplitude of that's the power spectrum. Okay? Nice. Then what we do? We have our delta. Delta are expressed by a linear term, a second order, a term at second order, and a term at third order. Okay? These epsilons, I introduce them to trace the order of the perturbations that we're going to use. And you can say, well, we don't need this one, right? Because we stopped ourselves at second order. But you will see that even though we will need a third order to have a power spectrum which is valid at second order. Okay? I'll show you now why. So let's get started. That's the construction. You can see that's f and f, but now the function is the specific one we are using, namely the density fluctuations. And we plug this guy here and the complex conjugate here. So that we have again the average outside here, and then we have these two products. Then we perform the product of this one times this one times this one times this one, and so on and so forth. And you realize that from the first terms, for example, these two guys, you get an epsilon to the power of 2, and then you get delta 1 and the complex conjugate. There is a plus the other terms, but the averaging and the sum are two linear operations. You can basically collapse it and get the average surrounding, capturing each product. Okay? Therefore, you can a sum of a sum is the sum of the individual sums. Okay? Just a linear operation. So you see this is this term, and then we have the other terms. For example, we have this, the term 1, which carry one epsilon and a delta 1, and this term that carries an epsilon to the power of 2, which gives us an epsilon to the power of 3. So now we have a third order, and then we have the epsilon to the power of 2. Okay? And like that for all the other terms. You have all combinations that come from this product, and you realize that if you consider the terms number 2 and number 2, you get an epsilon to the power of 2, epsilon to the power of 2, that gives you an epsilon to the power of 4. It means that the power spectrum, if I'm considering second order terms, I need to keep terms in the power spectrum, not in the density fluctuations. That's the difference. In the power spectrum up to fourth order. What does it mean? That I need the third order. Because if I multiply the delta 1, which carries one epsilon, and the third order fluctuations, which carries an epsilon power of 3, give me again an epsilon of the power of 4. Therefore, these two guys are at the same order. Therefore, if I would have neglected the third order, the third order, the fluctuations at third order, I would have missed a term which is as relevant as this one. Okay? Therefore, we need to stop here and drop the terms of the perturbation of the power spectrum, not the density fluctuation, again, stress the power spectrum of fifth order. Okay? That's quite an important step. We need the third order. Okay? Good. Then what we do? Well, we just have to compute. Then we will realize that because of Wick's theorem, terms that are odds, you see this is a 1, 1, that's 2. That's 2, 2, that's 4, that's 1, 3, again 4. Okay? Even terms are not equal to 0, but in the assumption of Gaussian random fluctuations, the even number are equal to 0. Okay? Because of symmetry between the fluctuations. Okay? When you average, gives you a 0. Okay? Good. So we need now to compute these different guys. Let's do that. And what we do? Well, this one we already know. That's the power spectrum in linear order. We already know how to deal with that. Let's give a look at the term 1, 2. 1, 2. I'll just show you what is the structure. of the equation, how do you obtain it? You obtain it by using delta 1, and then we have the delta 2 that are coming up from there. And then we just plug and these are how we computed in the previous lectures, right? So we have delta 2, that is, so we have the, sorry, this is the delta. So we have the delta 1, which is this one. We are not touching it. Okay? Then we plug here the result of our previous derivation, where we have that the perturbation at second order are given by the integral with respect to the two modes of a kernel, and then we have the fluctuations delta 1 that are entering at the second order. Okay? So all of these are the fluctuations at second order as we derived in the previous lecture. Okay? Then what we have? Then we can put everything together. So it is delta 1, we can bring it here. What does it mean? That we have delta 1, 1, and 1, 3 times for 3 different modes. We are now integrating over these 2 frequencies. Only k is free, and yes, it's fine, because that's the power spectrum depends only on that. This double integral, it's only required for the coupling between modes that we have seen before. So that's a reflection of the mode coupling that we had before. Okay? So you understand that 1, 2 is order 3 in terms of the fluctuations. And then the same you do for the other components, 2, 2, and 1, 3. Okay, no difference. It will turn out that this is equal to 0, but this is the simplest to show you how you do the mathematics. Again, very simple. Plug in here the results that we had from the previous equation, which is that. That's delta 2. Okay, and then you plug in this one inside. You have the averaging, which is here, but the average is commutes with respect to the integral, because they're both linear operations, and therefore the integral can be brought inside, because this is the only random variable. That's determined, that's determined. So these are just the given functions, these are random variables, and are the only one that remains within the averaging process. Okay? Nice. So we have 1, 2, so 1, 2, 2, 2, and 1, 3. Which are the ones that are relevant. We can move on. And at this point, we can assume Gaussianity. Okay? Means that each delta is drawn from a random probabilistic distribution which is given by a Gaussian. If you would have non-Gaussianity, you would have to need to draw deltas out of a non-Gaussian random distribution. Here we are assuming Gaussianity because they fit very well the data, and there is good motivation to do so also from a theoretical perspective, because that's what we expect from inflation. Good. Then, if we are assuming a Gaussian initial condition, so we are assuming Gaussianity, we can exploit Wick's theorem. Wick's theorem tells us that if we have an averaging between this product between a function and its only complex conjugate, can be expressed in this way. Well, you have your fluctuation multiplied by the value given by your probabilistic distribution. In this case, is a normal distribution. Okay, that's the Gaussian distribution that we are assuming. Well, this is the covariance, because your two modes, not meant they don't have the same sigma, okay, along the two directions, maybe is squashed and tilted. Okay, the covariance matrix carries this information. So it's just a multivariate Gaussian between modes, nothing more than that. Then this theorem tells us if we have like a triple product, we can write it like this, and because of the properties of the Gaussian, that's it, and the fact that we have these modes, that's equal to 0. If we are instead the product between function average, and again drawn from a Gaussian random distribution, this average of the product of 4 functions can be split in this way. Okay? I'm not going to prove Wick's theorem, just take it as given or look into that if you're curious about it. So what we do now? now we know how to deal with this sort of, now we know that one term is going to disappear, and for example, this one, that is ta 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 4 times, ta 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 4 times, we can split it like that. Okay? And we do that. Now we do that for the term 2, 2. Okay? I'm going to do that only for this one. For the other one, it's the same procedure, nothing fancy is going on, nothing different. Okay, so let's do that. So we have our averaging of our product, of our 4 products that are here. The rest are just the terms that we find here. So you see we have the 4 products. Where is it here? Where is it here? Then we have F2 and 2 repeated twice, and the 2 delta functions that are the relics of these deltas at second order. Okay, just what they are. So this expression is this expression here. Okay, I haven't done anything. But now what we do? We are using Wick's theorem, therefore we can use this guy here and split this average of 4 products into the product of average of 2, and the sum of averages of 2. Okay, Wick's theorem. Then we have this thing here. So you see that we have something relatable to the power spectrum. Therefore, what we can do is now substitute those terms, which are a product of 2 functions, one of which is a complex conjugate, with the power spectrum, and that is a delta function. So we plug it now here, where we have the delta, 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 delta. And that, you see, one is 1, 2, therefore it's equal to 0, again because of Wick's theorem. Same goes for 3, 4, because this makes 7, so it's again an odd number, also this one is 0, and they give you a 0. Then we have the first one, 1, 3, that gives you the power spectrum, and the power spectrum, and the 2 relative delta functions, you see with the 3 and the 4. Okay? And then the same is for the other terms. So you see that the averages are going to disappear. That's because we use the definition of the power spectrum. You see, we go from the average of this quantity to that. That's the result of the averaging processing. The power spectrum is the result of this averaging processing. Then we have the delta functions that we can exploit, because we have the delta function that tell us that K1 is equal to K3 and K2 is equal to K4. Therefore, we can rewrite this K3 and K4 in terms of K1 and K2. Right? Look at this delta, K1 is equal to K3. Therefore, I can write K and K1. K4 is equal to K2. Therefore, here I can write K2 instead of the K4. And so on in all the other places, where I can make the substitution. You see, 3 becomes 1, 4 becomes 2, and so on all over the places. Therefore, having done that, everything simplifies to this expression. Okay? But now we have other 2 delta functions to exploit, and we have that K is equal to K1 plus K2. Why I say plus? Because this is K minus the sum of the 2. Okay? Here and here. Therefore, I realize that K2 is equal to K minus K1. Therefore, I can just make this guy disappear, and I'm going to have only one integral with respect to K1, which is this one. Okay? So I just exploited the definition of I just used Wick's theorem, the power spectrum, and the delta functions. And all of this mess up here simplifies to that. What's the beauty here? That this second order term of the power spectrum depends only on first order terms of the power spectrum. It means that I can compute analytically the first order power spectrum, and so for free, sort of, I have the second order corrections. Okay, that's quite cute. And the same you do for the P1 3 terms. Therefore, we can exploit this one, we know that's the linear, then we can compute this is equal to 0 because of Wick's theorem, and then we have 2 and 3. We have our power spectrum up to second order, for fluctuations up to second order. and here is the summary. Okay, that's our beloved power spectrum at second order, one loop. Okay, just that. So again, I stress the fact that it depends on first order power spectrum. Okay, that's the perturbation of the density contrast. You can do the same for the velocity field. So what are you going to do? You define a power spectrum for the velocity field. And what you do? You plug into here the fluctuations up to second order. And then what you do? You keep for the power spectrum all terms up to fourth order, as we've seen before. And you do exactly the same mathematics. And you arrive at a power spectrum for the velocity perturbation up to second order. Okay? I don't repeat the mathematics because the pattern is exactly the same. So, what's the result? The result is that we are going to have the true power spectrum, if we want to call it so, for example, coming out from an embodied numerical simulation that captures all terms up to extremely high orders, which would be these black points. You see, these are the error bars because that's the power spectrum measured on the numerical simulations directly. Okay, is a theoretical model because it's coming out from a computer, pure numerical computation, but people are using a finite box. They cannot compute, an infinite number of universes. And because they're using a finite number of universes, there is an error on the measurement of the power spectrum. And it is larger, the error is larger for large modes, because if you have a box and you are considering this sort of modes, you have just few of them. Right? If you are at high K modes, you have a lot of fluctuations. And therefore you can have more of them within, so you have a wavelength, you have more of them within the box. And therefore the error bars are smaller. And then things kind of depart from reality because you're using a finite number of particles and you cannot go for a resolution which is within particles. Okay? You don't have information there and you have to stop. Good. In any case, black is the embodied numerical simulation. What this plot is showing is the ratio, so it's not the full power spectrum, but is the ratio between the power spectrum and the linear power spectrum where the wiggles have been removed. Okay? That's because it's nice to see the wiggles. It's a nice feature of the power spectrum and one want to see them. Right? If you remember the power spectrum, P, you have the K mode, is something like that. Right? It's going down, but then here I exaggerate a little bit the plot. You have the wiggles given by the baryonic acoustic oscillations. Right? These are the oscillating modes. Gives you these wiggles here. So what people do is to basically use as a reference for the linear spectrum, not this guy, but this guy. Okay? Such that if you do the P linear power spectrum dividing the P non-wiggle power spectrum, which is the red one, what you see is something like that. So it's 1, because the ratio is 1 up here, and then where there are the wiggles, you're going to see the fluctuations. Okay? That's this line here. So it's here, and then boom, it deviates. Okay? Sorry. So the non. So exactly. So that's this one. So the ratio between the linear and the power spectrum is aligned like that. Okay? Fluctuation, which is this one. So this would be your linear approximation for the power spectrum. If we include the one loop term, you can see that it follows much better, which is this blue line, it follows much better the curves. For example, you see that this guy is here, but the points are up here. Okay? If we are using the one loop spectrum, at this mode, the one loop power spectrum is exactly superposed to the black ones. Here is good. If we continue, it's still good, still good, still good, still good, still good, it's going, pan departure. Now you see that we are failing. We can move to higher case, because the linear regime was fine only here, we can move up to here. But then we fail, and things go crazy at higher frequencies. Okay? High frequency, smaller scales. There are then correction terms that I'm going to describe later, and makes the situation much better. Okay, so what we're going to do, we can basically describe everything up to here. That's because in what I'm going to show you later, we are going to consider further terms that enter into the observations and further terms that we neglected during the derivation. Because, for example, we consider only irrotational velocities, right? We consider only velocities of this sort. We were not using this sort of motions. Okay? That's one of the approximations that we did in the derivation. And they occur whenever the collapse is quite in an advanced stage. So you understand, there is angular momentum conservation, we spoke about that. So in the linear regime you have your collapse, but then when you are approaching, things start to orbit one around each other, right? And these are irrotational modes that we completely negated. They occur in high frequencies where the linearity starts earlier, and therefore, whenever we're going to include them, we can go from here to here. Okay? Nice. Now look what else we can see this plot. That's for redshift 0, so nowadays, and here we are going back in time up to redshift 2. And what do you see? You see that we have our linear power spectrum, we have our data, and now the linear power spectrum is correct up to here. Before, for the linear regime, we had to stop somewhere, let me say, here, which would be here. At high redshift, you can see that we can go to larger modes, because the null linearities are not yet present at that, or at those scales. Okay? Good. So you can see the time evolution and the growth, the nonlinear terms. And here you can see the limit at which you can use our approximations. As a function of redshift, these are the k modes. If you are at larger k modes for small scales, with all the approximation we used, you shouldn't go here. You can, at this redshift, you should stop at 0.5. At this redshift, you should stop at 1.3 or something, and then at redshift 4, you can be on even on smaller scales, up to 0.5, and so on and so forth. Okay? The limit of validity, and that's what we achieved so far. Okay? Good. Let's now arrive at the bias. Okay? Here I can go back to the blackboard for a bit, because it's sort of manageable. And some equation, again, I'm going to show you at the beamer, because they tend to be quite big. Okay? So we can have a break, we can resume at 20 past midnight.